Bismillahirrahmanirrahim. This is an exercise about sets, power sets, and application maps. Let E be a set, any given set. P of E, the set of all sets of E, power set of E. A and B are two subsets of E. We consider an application F from P of E towards P of A times P of B, power set of A and power set of B, such that for all x from P of E, an element from P of E, the image is f of x, which is equal to f of x, which is equal to x intersection A and x intersection B. The first question, we characterize the injection. So F is injective if and only if A union B is equal to E, and F is surjective if and only if A intersection B is equal to empty set. Then we give a characterization such that F is bijective. We start with this question. First, we suppose that F is injective, and by contraposition, we suppose that A union B is different from E. Let X belongs to E minus A union B, since they are different. And we consider F of this element. This is equal to what? X intersection A equal to empty set, and X intersection B is equal to empty set. But this, the same image is the direct image of the empty set. This one and this one are not equal, and we suppose that F is injective. So F isn't adjective, such that A union B is different of E. A union B equal to E. This is necessarily condition for B to be injective. Inversely, we will take the inverse. We will suppose that A union B is equal to E. Then this will implies that F is injective. Now, sufficient condition, we suppose that A union B is equal to E. This will implies that what? Will implies that F is injective. Let X and Y be two elements of P of X, such that what? Such that F of X equal to F of Y. This means that X intersection A is equal to Y intersection B, and X intersection, I feel that something is wrong. X intersection B is equal to Y intersection B. This implies that if we take the union between them, we will get A intersection X intersection A union B equal to Y intersection A union B. Since we suppose that this is equal to E, this is equal to E, and this is equal to E, which means that X is equal to Y. So this is the sufficient condition. We prove this first question. About the second question, F is surjective if and only if the intersection is equal to phi. We suppose that But what? That A intersection B is equal to the empty set. And we prove that F is surjective. Let A1 be an element from P of A and B1 be an element from B of B, such that F, can we find, does that exist an element X from E, or X from P of E, such that what? Such that F of X equal to A1 B1. This is the question. What we have, this is true. So, if we take, after thinking, if we take X equal to A1 union B1, this choice will fit with our question. Why? Because F of X, which is equal to A1 union B1, this is equal to what? This is equal to, this is the X, so A1 union B1 intersection A1 and A1 union B1 intersection B1 A1 union A1 is equal to A1 intersection A1 is equal to A1 union B1 intersection A1, this is equal to empty set. Why? Because A1 is from E and B1 is from B. Since these greater are empty, the smaller will be empty. This is equal to A1 intersection B1, this is an empty set, union B1 intersection B1, this is equal to B1. Why A1 intersection with B1 is empty set? Because A1 is in A and B1 is in B. This means that the intersection is an empty set and this one is equal to B1. So, therefore, thus we find X from E such that they are image of X. This means that if the intersection is an empty set, this implies that F is a surjective one. Conversely, we suppose now that F is surjective and we have to prove that the intersection should be empty. We suppose that F is surjective. Then we prove that A intersection B is an empty set. F is surjective. What we can do? Let an element X from A. And let us consider X and empty. These elements belongs to what? Belongs to P of A times P of B. They are elements from this. For this implies that there will exist an X from P of E, such that what? Such that they are image, such that F of X is equal to X intersection A and X intersection B. But this image is equal to X and phi, empty set. Don't forget that X is an element of A, but X intersection B means that the X is an element of A. X is an element of A. This means that X is in A and X is in capital X. And X belongs to capital X, and the intersection is equal to empty set. This means that X isn't in B. So from this, we deduce that X belongs to A by hypothesis, and this implies that X isn't in B. This means for each single X from A, we can do this. It is a known one, any given one. This means that A intersection B is an empty set. So we proved the second implication. What we need to do to finish this exercise? We need to give a characterization to this function to be a bijective one. F injective is equivalent to this, and F surjective is equivalent to this. So F bijective is equivalent to A equal to the complementary of B in E, or equivalently B the complementary of A. This is, we denoted it by the closure, and we denoted it by the closure. Why? Because we have A union B equal to E, and A intersection B equal to the empty set. These two conditions